Let's spend a few minutes this morning reviewing the relative motion stuff that we did on Monday. Remember relative motion? We said motion relative to something. We have to define what our motion is relative to. Now, typically in the past, we haven't done that, at least not explicitly, but implicitly we have. Okay, when we asked, remember the very first problem that you had this year, the question was, how long is it going to take Mr. Dickie to go from Regina to Calgary if he's averaging 100 kilometers per hour and it's 750 kilometers away? Okay, that was the first real question you had using an equation this year. We didn't talk about a frame of reference. We didn't talk about what our velocity was relative to or any of that sort. But implicitly, we knew that that velocity was relative to the Earth. It wasn't relative to the moon. Okay, it wasn't relative to some train on the tracks in Saskatchewan. It wasn't relative to the sun. Okay, it was relative to the Earth. Now the Earth is moving at several thousand kilometers per hour. So if we want to make it relative to the sun, then my velocity would have been dramatically different than it was when I calculated it on that first day or that second day of class. Okay, we made it relative to the Earth. We didn't think about that, but that's what we did. We always have to have a frame of reference. We always have to have it relative to something. Okay? An example that maybe makes a little bit more sense why we have to be relative to something, say we're walking on a train. Okay, a train's going at 20 kilometers per hour to the east. I'm walking on that train at 5 kilometers per hour. My velocity relative to the train is 5. My velocity relative to the Earth could be either 25 or 15, depending upon which way I'm walking on the train. Okay, that's clear in that case that we have to be very explicit in how we define the velocity relative to either the Earth or relative to the train. When we're finding a relative velocity, a velocity relative to the ground, we have to add vectors together. Okay. In the case of the train example, that's an easy one. Okay, if I'm going 5 kilometers to the east, 5 kilometers per hour, I should say, to the east, and the train is going at 20 kilometers per hour to the east, then my velocity relative to the ground is 25 kilometers per hour. I add those two vectors together, I'm done. If my velocity is 5 to the west, and the train is 20 to the east, then my velocity relative to the ground would be 15. Again, I add these together, but of course the 5 kilometers per hour becomes a negative value because it's to the left. When I'm finding a relative velocity, I always add vectors together. But, as we learned on Monday, when we're finding a relative velocity in 2 dimensions, it's a little bit trickier because the normal rules of addition don't work. 20 plus 5 doesn't necessarily equal 25 or 15. Let's say that I'm walking, the train, is going at 20 kilometers per hour to the east, but I'm walking across the train. I'm walking not from end to end, but I'm walking from one side to the other side. Yeah, I'm walking 5 kilometers per hour to the north. What's my velocity now relative to the Earth? Still going to add these up, but I'm not going to add them up according to the rules of scalar addition. I'm going to add them up according to the rules of vector addition. In other words, I'm going to say the resultant vector, which is the sum of these vectors, that is my resultant velocity. Okay, the velocity relative to the ground would be the square root of 20 squared plus 5 squared. So when we're finding that velocity relative to something, we always have to add vectors together. It's just a matter of whether we're adding them together in 1 dimension, 20 plus 5 is 25, or 20 plus 5 is 15, or we're adding them together in 2 dimensions, where 20 plus 5 is the square root of 20 squared plus 5 squared. Now, if you get this vector diagram drawn, okay, it's relatively straightforward where we're going to go from there, right? We do the Pythagorean theorem, we do the inverse tan function. But sometimes it's a little bit tricky to get that diagram drawn. So we break it up into 2 categories. We break our vectors up into 2 categories to help us to draw this vector diagram. The 2 categories are solid line vectors and dotted line vectors. You can see here that I have 2 solids and 1 dotted. The dotted is my resultant velocity. It's the resultant vector. It is the velocity relative to the ground, my actual velocity. My solid line vectors could come from aiming in a certain direction. Okay, if I aim, let's say I'm a sharpshooter in the Army, okay, and I aim my gun in a certain direction, but there's a crosswind that's pretty strong. Okay, I aim in a certain direction. The bullet that I aim has a velocity of, let's say, 400 meters per second to the north. We would draw that as a solid line vector because that's where I'm aiming. The wind that's blowing to the west would also be a solid line vector. The actual velocity of the bullet, or the velocity of the bullet relative to the ground, would be my dotted line vector, my resultant vector, okay, my relative velocity. Another example of a solid line vector would be heading. Okay, the captain of a ship heads directly west across the river, but there's a river current going to the north. Well, he doesn't actually end up going directly west. He's just heading that way. Heading west would be a solid line vector. The river current would be a solid line vector. And where the ship actually goes would be a dotted line vector. Let's say you're flying an airplane and you want to go directly north to Edmonton. Not here, look up here. You want to go directly north to Edmonton. But there's a wind to the west. Where do you have to aim? Well, where we want to go directly north is going to be a dotted line vector. Okay, we draw that as a dotted line vector. The wind is going to be a solid line vector. Okay, where we're heading, or where we have to aim to get directly north, is once again going to be a solid line vector as well. Let's say that the airspeed of an airplane is 800 kilometers per hour. Okay, that's how fast it can travel if there is no wind. So you get a problem where it says the airspeed is 800 kilometers per hour, and then it goes on to talk about a wind and blah, 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 blah. The airspeed, or that speed without wind, would be drawn as a solid line vector. Okay, the wind would also be drawn as a solid line vector. Where the airplane actually goes, or where the airplane wants to go, or the velocity of the airplane relative to the ground, would be my dotted line vector. We did an example Monday, I guess it was. Okay, a relatively straightforward example. We're going to partly go through this again. Not going to solve it mathematically, but we're going to set it up according to the solid and dotted lines. And then we'll go to another example that we haven't done yet. It says the pilot of a plane heads directly north to Edmonton. Heads north to Edmonton. That's a solid line vector, right? Heads north. That contributes to where the pilot actually goes. It's not where the pilot goes, though. The pilot aims or heads north. Where do they actually go? We don't know. Okay, we don't know. Where's the dotted line vector right now? We don't know. But we're heading north. That's going to be a solid line vector. So let's draw that as a solid line vector. Okay, we got 200 kilometers per hour to the north. There's a wind of 50 kilometers per hour to the east. We're going to also draw that as a solid line vector. Because wind isn't where we actually go, wind contributes to where we go. Okay, solid line vector. We want to add these together. Let's draw it front to back as we have for the last week or so. And then let's draw a resultant vector, our dotted line vector, from start to finish. Where does the plane actually go? Well, the plane actually goes right there, wherever that dotted line vector is and whatever the speed of that dotted line vector is. Let's do another example, one that we haven't done yet. This one says the captain of a ship aims her ship east at 20 kilometers per hour, but there's a current of 10 kilometers per hour that puts the ship off course. Where does the ship actually go? You guys, those of you who drive, how many people drive here? How many people have a driver's license, whether it's a learner's permit or, okay, so more than half of you. You guys know that if you're driving and it's really, really windy, you get this crosswind blowing across the highway. Look at your steering wheel. Okay, when the wind is blowing this way across the highway and you're trying to go north like this, your steering wheel is turned way to the west, right? You guys ever notice that? You're turning to the west. You're aiming to the west to compensate for that wind to the east. Okay, the solid line vector would be the direction you're aiming, the direction you have your steering wheel turned. The solid line vector would also be the wind. The dotted line vector would be the direction you actually go on the highway. Here, we have a solid line vector where the captain of this ship is aiming her ship 20 kilometers per hour to the east. There's a current of 10 kilometers per hour, which should say, by the way, to the south. I just forgot to put that in there. A current of 10 kilometers per hour to the south that takes her off course. Where does she actually go? Well, that 10 kilometers per hour is also a solid line vector because it's not where she actually goes. It contributes to where she goes. It helps give us the final velocity or the resultant velocity. We can draw that either here, or we could have drawn it like this. Either way would have worked, right? Because both ways are drawing front to back. Either way works fine. The resultant velocity, where the ship actually goes, is my dotted line vector. So let's draw that from front to back, from back to front, I should say, from start to finish. Let's label it as R, and then let's put the angle in there as well. Where does this ship go? Let's find the value of R by saying 20 squared plus 10 squared. Square root that. It's going to be the square root of 500. Which lane is going to give me, I'm sorry? Oh, 24? 22? 22 kilometers per hour. We're going to find the angle here by saying the inverse tan function of opposite over adjacent, that's 10 over 20. What does that give me? .5 or 27 degrees, and that would be south of east. This should be logical, right? You've got this river or something that's got a current of 10 kilometers per hour to the south. You're aiming across this river at a velocity of 20 kilometers per hour. You know that you're not going to end up going straight across the river. Intuitively, we know that. Okay, if you're standing on the side of the river and you're looking straight across and you can see a current going down the river and you want to swim across the river, you know that if you swim directly across, you're not going to end up directly across. You're going to end up downstream somewhere. Okay, that's what happens here. Okay, we got a solid line vector where we aim, another solid line vector, which is our river current. Okay, they combine to give me where we actually go. Intuitively, you know that if you aim directly across the river when you're swimming and there's a river current going downstream, you're going to end up across the river, but you're going to end up downstream of where you started. Does that make sense? Let's keep straight those solid line vectors and those dotted line vectors, but also let's, in the back of our head as we're doing these questions, think, does it make intuitive sense? Sometimes we leave that. We leave the intuition off to the side. We don't pay any attention to it. Okay, at some level, we know that we're going to end up downstream from where we started. So if you draw a vector diagram and it doesn't end up downstream, well, you know you've done something wrong. Let's try one more. This one says the airspeed of an airplane is 800 kilometers per hour. Airspeed, do you guys remember what that means? The speed of the airplane without wind. Is that solid or dotted line? That's a solid line vector, right? We don't know what the direction is here right now. Okay, so we can't really draw it yet because we're not told whether it's north, south, east, or west, or whatever. The pilot aims his plane west. Okay, that's a solid line. Aims west. But there's a 75 kilometer per hour wind to the south. That's also a solid line vector. Wind. Wind isn't where we actually go. Wind contributes to where I actually go. So that's going to be a solid line vector as well. What's the ground velocity of the airplane? Ground velocity is the velocity relative to the Earth, which is my actual velocity, which is a dotted line. Now it looks like I've got three solid lines here. In none of these problems will you ever have three solid lines. So how do we resolve that? How do we turn this into two solid lines instead of three? Hayden? Good. We're combining the 800 with the west. We're heading to the west. Now, if there's no wind when we head to the west, how fast are we going? 800. So let's draw that. 800 kilometers per hour to the west. We have a 75 kilometer per hour wind, which is also my solid line vector that's to the south. What's the velocity of the airplane relative to the ground? Draw it from start to finish there as our dotted line vector. Let's label R, let's label theta. R is 75 squared plus 800 squared. Don't forget to square root that. We end up getting 803, which actually rounds 8.0 times 10 to the 2. So the velocity of this airplane, due to its speed in still air and the wind, is not dramatically different than it would be if there was no wind. That's because the wind speed is so much slower than the speed of the airplane is. It's slightly different, but to the right number of digits, it's the same value. Let's find theta, though. It's the inverse tan function of opposite over adjacent, 75 over 800. When we do that, we end up getting 5.4 degrees. And this would be south of west. Right? We went west, then we went south, so it's south after west or south of west. So we're not hugely off course here. We're only 5 degrees off course. But you can imagine if you're the pilot of an airplane and you're trying to fly somewhere, you don't want to end up 5 degrees off course. Okay, you don't want to look down all of a sudden when you're supposed to be in the spot you're supposed to be, and then look over a few miles to the left and say, oh, there's the airport. Oops, missed. Okay. We want to be able to account for the wind so that we end up where we're supposed to be going. You can see how this is a pretty useful skill if you're a pilot or you're the captain of a ship, or even, for that matter, if you're trying to swim across a river. You're not going to sit there with your calculator when you're trying to swim across the river and calculate where you need to aim. But at some level, you're going to intuitively know where you're going to have to aim. You're going to draw that vector diagram in your head and analyze it qualitatively like that. All right, I'm going to give you a worksheet here, and I'm going to ask you to do, please, the first 3 questions on the worksheet here over the next few minutes at your desks, okay? I want to take a look at question number 3 here. Number 3 says a boat whose speed in still water is 2.5 meters per second is in a river that's flowing at 1.2 meters per second to the south. Okay, let's label what our solid line vectors and our dotted line vectors are going to be. Still water, that's a solid line vector. A river current, that's a solid line vector. We want to find the velocity of the boat relative to the shore, or in other words, the velocity relative to the ground, the actual velocity. That's going to be our dotted line vector. Now, this is going to be our solid line vector as well. So it looks like we have multiple solid line vectors, but in the end, the speed in still water is tied with that direction here. Okay? In other words, we're heading at 2.5 to the south. We're heading at 2.5 to the north, or we're heading at 2.5 to the west there. So this goes with this one goes with this, and this one goes with this as well. For the first 2, we don't really have to draw a vector diagram if we don't want, because it's all one-dimensional. We still have to add vectors, but it's easy to add these vectors. Look, we get 2 solid line vectors. One of them is 1.2 to the south. One of them is 2.5 to the south. We want to add those together. We don't need to draw a vector diagram or do a triangle. all we do is add them together and literally say it's 3.7 meters per second to the south. Okay, question A is done. Question B, we also have two solid line vectors. This time, we've got 2.5 to the north, and we've got 1.2 to the south. We can add those together as well without drawing a triangle. 2.5 plus negative 1.2 gives me 1.3 meters per second to the north. Now finally, the third one, where the boat is headed west. This time we have 2.5 to the west, and we have 1.2 to the south. Now, to add these two vectors together, because we're in two dimensions, we have to draw that triangle. So let's draw it. We got it front to back here, and then we've got our resultant vector drawn from start to finish. Okay. 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 Thank you. Remind me to give these to you here, guys. In a minute. All right, back to this here, guys. We're looking for a resultant vector here now. Okay, we got a triangle. We have to draw a triangle to add these two vectors together. So we draw our triangle, we label our angle, we label our resultant. R is going to be equal to the square root of 1.2 squared plus 2.5 squared. Okay, we solve that, we get, what do we get when we do the math on that? What do you get there, Wayne? 2.77. We're going to round that to 2.8 meters per second. So where does the boat, what's the velocity of the boat relative to the shore? Well, the boat ends up actually going faster relative to the shore than it can when it's in still water, because it's helped along by the river current. Right? The river current speeds it along by an additional 0.3 meters per second. Now we're going to calculate that angle as well by saying it's the inverse tan function of opposite over adjacent. What's the inverse tan of 1.2 over 2.5? Who would have the answer to this question? Lane? Yes. What is it? 0.692? I think you might be in radiant mode or something. Yeah. Somebody check that, guys. Inverse tan of 1.2 over 2.5. Well, what do we have there? 25.6, or we're going to say 26 degrees. This would be south of west. So we're aiming to the west, but there's a river current to the south, so where do I actually end up going? South of west, 26 degrees, in fact, south of west. All right, I would like you guys to take another 2 minutes, please, and take a look at question number 4 on the back of that page. All right, let's take a quick look at number 4. This one says an airplane is traveling east at an airspeed of 150. So in other words, in the absence of wind, it can go 150 to the east. Okay? It's aiming 150 to the east. 30 meters per second wind is blowing north. What's the velocity of the plane relative to the ground? This is going to be a solid line vector. This is going to be a solid line vector. This is going to be a dotted line vector. Okay, we're aiming, or we're heading 150 to the east. Let's label that. There's a wind blowing of 30 meters per second to the north. Let's label that. Our resultant vector, drawn from start to finish here, our dotted line vector, the velocity of the plane relative to the ground, is the hypotenuse. So we're going to say r is equal to the square root of 150 squared plus 30 squared. And then theta, the angle at which we end up going, which is important because this is a vector, so we need a direction. The angle is going to be the inverse tan function of opposite over adjacent. What do we get for r there? We get 153 meters per second, which is going to round to 1.5 times 10 to the 2. 2 digits, because we have 3 digits here, 2 digits right here. 1.5 times 10 to the 2 meters per second. So to 2 digits, it ends up being the same speed as we were going before, the speed in still air. Well, that's because the wind speed is so small compared to the airspeed of the airplane. What do we get for the angle there when we calculate that? Or 11 degrees. And this would be 11 degrees north of east. Okay, in my vector diagram, I'm going east, then I'm going north. I'm going north after east, or I'm going north of east. Had you drawn that y then x, you would have gotten 79 degrees east of north, and that would have been just as correct. Okay, now I'd like you to take a look at question number 5. Question 5, 5a isn't overly tricky. It's no worse than questions 1 to 4. Question 5b and 5c are a little bit more challenging. Okay, I want to see what you can do with 5a, of course, but also want you to give 5b and c a try as well. We'll go over that one in a few minutes once you've had a chance to give it a whirl here, okay? Everybody look up here now, please. I want to take a look at question number 5. 5a is no harder than question 4 or 3 or 2 or 1. 5b and c are a little bit harder. Let's identify what our solid line vectors are and our dotted line vectors are first. Captain of a ship aims his ship with a velocity of 25 meters per second directly north. That's going to be a solid line vector because we're aiming there. It's not where we're really going. That's where we're aiming. That contributes to where I'm going. So it's solid, not dotted. There's a river current of 8 to the east. That's also going to be solid. Okay, the river is 850 meters wide, which is really irrelevant for question A. We want to know what the velocity of the ship is going to be relative to the shore. In other words, we want to find our dotted line vector. So let's do this. Okay, let's draw this river out here. There's my river. He's aiming directly north across this river at 25 meters per second. There's a river current of 8 meters per second to the east. We want to find the velocity of the boat relative to the shore. So we want to find this dotted line vector, this resultant vector here. Okay, that seems pretty straightforward. R is going to be equal to 25 squared plus 8 squared. We're going to square root that. 625 plus 64 is 689 squared root of 689 is going to be somewhere in the range of, I'm going to say 27. Is it 20? 26? Okay. Let's say 26. Okay. 26.38 meters per second, which rounds to 26 meters per second. Now the angle is going to be found by the inverse tan function, as always, of opposite over adjacent. 8 over 25. What does that give me for an angle there, Josh? 18 degrees. And this is going to be 18 degrees west of north. Now we go north, then we go west. We went west after north, or west of north. You could have drawn it the other way, drawn the 8 and then the 25, and you would have gotten an angle of, sorry, it should be east of north. Should be east of north. You could have drawn it the other way, though, and you would have gotten a value of 72 degrees north of east, as opposed to 18 degrees east of north. Both are correct. Now, the time that it takes the ship to cross the river, this is a tough question. Now is when we're going to label the width of the river, but on a separate diagram. The river is 850 meters wide. I want to find the time that it takes. Laura asked me a question just a couple minutes ago. She said, okay, I want to use v equals d over t for this. Okay, good. Good thinking. She wants to use v equals delta d over delta t for this. She wants to find time, so she's going to rearrange that. Time goes up by multiplying, v goes down by dividing, I end up getting d over v. Okay, that's good. Let's use 850 meters for my distance, or for my displacement. But what velocity do I use? I got 25, I got 8, and I got 26.38. What velocity do I use, Fraser? 25. Velocity and displacement are both vectors, and in the same equation, they have to be the same direction. So if I'm using 850 to the north, I have to use my velocity to the north. Now, Josh showed me how he did it a few minutes ago here, and he didn't actually use the 25 meters per second to the north. He used 26.38 meters per second. But Josh also didn't use 850 meters. Josh used this distance diagonally. Now, what was that distance, Josh? He used the angle in the 850 to find what that distance was. 890 something. Okay, that was also correct. Okay, it was correct for Josh to do that because if he used a velocity at the angle, that's okay as long as he's using the displacement at the same angle. Okay, I used the displacement straight across, well then I got to use the velocity straight across as well. You just got to be consistent. If you're using straight across displacement, that's great. Use velocity straight across. If you're using the velocity at an angle, that's great. Use the displacement at an angle. Doesn't matter. Gets you the same answer. This works out, by the way, to be 34. Is it 34? 34 seconds. All right? Now, finally, gentlemen, let's solve question C here now. Question C asks us for how far downstream the ship ends up when it reaches the other side. Well, if I have 850 across as a displacement vector, and I know my, I know that my time here. Let's do this a little bit differently. Okay, if I know my time is 34 seconds, and I know my velocity downstream is 8 meters per second, then I can find my displacement. V is equal to displacement over time. Rearrange that to solve for displacement. I get D is equal to V times T. V is 8 meters per second. T is 34. 8 times 34 is, what is it? 270, did you say? 272? 2.7 times 10 to the 2 meters. Why does that work? Because again, my velocity was downstream. My displacement will be downstream. Why is it that I could use time here, though? Okay, if I'm using displacement across, then I need to use velocity across. If I'm using velocity downstream, then I get displacement downstream. Why could I use the same time going across as I did for downstream? Why could I use the time in both the x and y? Whereas velocity and displacement I couldn't. What's the difference between time and velocity and displacement? Time is a scalar. So there's no reason why I can't go from here to here with time, but I can't go from here to here with displacement or velocity. Okay, does that make sense? Okay, we're going to try to get one more example in here so that we can give you a couple questions for homework here. And then that'll be it for the day for us. So it says the pilot of an airplane wants to go directly north at a velocity of 500 kilometers per hour. Wants to go directly north. Doesn't go directly north. Or doesn't aim directly north, I should say, but wants to go directly north. When we want to go north, that's going to be a dotted line vector. Okay, the pilot of an airplane, and you want to go to Edmonton. Okay, you need to plan your trip so that you end up in Edmonton. You need to compensate for the wind so that you end up in the place you want to end up. There's a wind to the east of 85 kilometers per hour. That's a solid line vector. What's the velocity, including direction, at which the pilot must aim? Okay, that's going to be a solid line vector as well. But we don't know what that is. We know that we want to go north at 500. That's a dotted line vector. Let's draw that in. Okay, it's kind of odd that we're drawing our dotted line vector first, but since we know the value of where we want to go, our dotted line vector, then we have to draw that first. Now we also have a wind that's a solid line vector of 85 kilometers per hour to the east. When we combine that with our dotted line vector, where are we going to put it? I'm going to give you 4 positions. Am I going to put it here? Position 1, position 2, position 3, or position 4? Where do you want to put that 85 kilometer per hour vector to complete this vector diagram? Position 1. What happened there? There we go. Position 1, position 2, position 3, or position 4. I'll give you a hint. There's actually 2 answers that could be correct, but one actually ends up being easier. Position 2, so up here. Who agrees with that? Okay. That's not right. Why not? Because dotted lines have to go start to finish, or dotted lines have to go front to front. Okay? Dotted lines can't be drawn like the other vectors. Okay, if we had 2 solid lines, then that would be perfect, Bo. Right? Front to back would be absolutely perfect. But a dotted line can't be drawn front to back like that. So that doesn't work. If position 2 doesn't work, then let's try position 1. Is that okay? Yeah. Yeah, that's fine. Because dotted line vectors have to go from start to finish. If I draw my solid line vector in position 1, and then I draw my other solid line vector right here, then you can see that my dotted line vector goes from start to finish. Now, what am I looking for? I'm looking for this one right here. Where do we have to aim? Just hold on 2 seconds, we'll finish this off. Where do we have to aim? In order to go straight north with a wind to the east, we have to aim where that green vector is. How do we find that? Well, it's just as easy as the other questions were, right? It's just not the resultant this time. It's still the hypotenuse. It's just not the resultant. Just hold on. Have a seat, Travis. Just have a seat. Let's find what the value of that is. 85 squared plus 500 squared. Let's square root that. Let's find the angle here at which I have to aim. It's equal to the inverse tan function of opposite over adjacent, 85 over 500. Okay, whatever we get here, we won't spend the time here since the bell's gone to figure out what the actual value is. You can do that. That's the method that we'd use. Be careful with those vector diagrams, okay? Dotted line vectors can't be drawn the same way as the solid line vectors are. So make sure that you accommodate for that when you're drawing those vector diagrams. Your homework for tonight. Your homework for tonight is question 6, and we'll go questions 6 and 7 on your worksheet. Questions 6 and 7 on your worksheet, please. That's it for today. We'll see you tomorrow.